Yeah, so in 1935, we knew about these kits, the non-commuting observables. Heisenberg had his native quantum mechanics. Schrodinger had his wave function picture. Now you know the relation between the two. And there was one weird phenomenon that we talked about, which is the idea of a superposition, right? You could be in a superposition of two vectors. And we said this points to some inherent uncertainty in nature. And this is not our lack of knowledge. This is different from probability distributions, right? So Einstein was bothered by this, and he tried to cook up a paradox with the help of some logicians, some mathematicians, I think they were logicians. And he came up with some notion as an objection to quantum mechanics, a weird phenomenon called entanglement. It turned out that Einstein was up to something. And the answer to this question is, can a quantum description of reality be complete? Yes, but there's something weird to quantum mechanics beyond superposition called entanglement that we're going to discuss throughout this course and we're going to get there. But before getting there, we'll have to generalize our notion of what a state is. So recall the axioms of quantum mechanics. We're going to go over them again. And this is around the same time, 1935, Princeton, New Jersey. There was a mathematician called von Neumann who wanted to put quantum mechanics, this new physics, on solid foundation. He was a mathematician, so he came up with a theory of quantum mechanics. He has a book, again, 1935, Mathematical Foundations of Quantum Mechanics. And in that book, he realized that the right way to define a state is a density operator or a density matrix. So that's the topic of this lecture, right? And the fact that density matrices, at first, they might look like innocent looking, but by the end of the course, we learned how it all ties in with this entanglement phenomenon and why it's very, very crucial to understand density matrices. So this next step we're going to take, at first, it might look innocent, but it's actually very, very profound in quantum mechanics. All right, so that's the idea. We're going to generalize our notion of a state in quantum mechanics today. Is that good? As usual, I'll start with a review of lecture 8, previous lecture. If there are any questions, please ask at any point. So the title of this lecture is General States. Oops, no, I don't want to record. General states are density matrices. You might hear density operators, you might hear density matrices. So we're going off of the Sakurai text. They're on page 174 or 147 of Sakurai. There's a discussion of this, but the importance of density matrices have become more and more important in the past 2 decades, to a point that nowadays, even though if you pick an old textbook from quantum mechanics, it probably has no discussion of density matrices. Nowadays, it's impossible to remove it from chapter 1. It's a big, big part of it. You might have heard about quantum technologies, quantum information. Density matrices are the heroes of that story. So that's why I'm squeezing it in chapter 1. All right. So review of lecture 8. We talked about psi alpha of x prime, which is a bracket of x prime, the delta function normalizable eigenket of the position operator with eigenvalue x prime, and some arbitrary ket alpha. We call this the position space wave function of ket alpha, right? So this is what Schrodinger came up with, wave functions. And we've had descriptions of these in terms of matrices as well, right? Then we talked about, well, if you take the same kit, you could expand it or take the overlap of it with the eigenstates, eigenstates of the momentum operator. If you recall, momentum operator generated translations in X. So it was canonically conjugate to the X operator. And this is the momentum, the same wave function, the same state, but the wave function corresponding to the same state and momentum space. So the state is the ket alpha, right? These are different descriptions of him from the point of view of different observables. Is that good? All right. Then we said it's easy to, we related these two pictures, position space and momentum space wave functions. And we said they're the Fourier transform and Fourier and inverse Fourier transform of each other. And in that story, what played an important role was the observation or the derivation that this overlap is the exponential of e to the power of I p prime x prime over h bar 1 over square root 2 pi h bar. This was a crucial piece of the derivation, the argument. Any questions? We talked about Gaussian states. I think it was, I'm not recalling whether it was last lecture or previous lecture, the one before. But we talked about the Gaussian states saturating the uncertainty relations. Now, for those of you guys who are going to get a little bit deeper into quantum mechanics later on, you are going to learn that there is a deep sense in which Gaussian states are classical. Now, we're not going to have time to discuss all of that, but there's a sense that Gaussian states are more classical. This statement could be made rigorous. All right, good. We talked about wave packets, right? We said that the Fourier transform of a Gaussian is a Gaussian, which means that a wave function that's Gaussian in space is also Gaussian in momentum space. Physical spatial directions is also Gaussian in momentum space. But if you try to make the wave packet peak in one coordinate, in the conjugate basis, it's going to get really wide, right? And that has a manifestation of the uncertainty relations. Questions? All right. Then we talked about the postulates of quantum mechanics. So we've mentioned 4 postulates for quantum mechanics. The first one dealt with states and observables. The second one dealt with measurements. These are the 2 that we've gone over. And then how did I formulate them? The third one was about evolution, right? And the fourth one was composite systems. Yeah, I think that's how it goes. So we're not going to talk about 3 or 4. Today we're going to talk about postulate 1 and how we absolutely have to generalize it. All right, so what was postulate 1? Let's recall. It said that associated to any isolated physical system is a complex vector space with an inner product called the Hilbert space. I'm being a physicist. I should put a complete inner product, but it doesn't matter. It's the state space of the system. The system is completely described by a state vector. The keyword here is vector, right? A unit vector in the Hilbert space. Every measurable physical quantity, quote unquote, observable, is described by a Hermitian operator. You recall that Hermitian operator means that it's self-adjoint. The operator and its adjoint are the same. You should also by now realize that a Hilbert space comes as a vector space, comes with this adjoint, right? So the Hilbert space is the space of kets and is identical, isomorphic in mathematical terms, to the conjugate space, which is the space of Broad that we usually write as H star. Good? All right. So that was the, are there any questions about this this postulate? Today we're going to see that kets as vectors in the Hilbert space are special, very, very special states in quantum mechanics. A general state is something that we're going to call a density matrix. We're going to motivate it, we're going to describe it. And then the kits as special density matrices are going to become pure. A density matrix describes, or a state, a state or density matrix describes a ket if and only if it's pure, right? Purity is a statement of whether the state is pure or not, is the statement of whether it could be described by a ket or not, right? A general density matrix that's not pure, this is just terminology, is going to be called mixed. Good? So this, I'm just saying a terminology, we're going to define it, right? So the class of states is huge. They're very, very special states. These are all density matrices. Very special subset of them. I don't want to draw anything because this is a set of measure 0. Is described by kets, and these are vectors, and then we call them pure states, as opposed to mixed states. Is the terminology clear? We're gonna define the measure. How do you tell whether state is pure or not? Good. All right. So just for completeness, let's go over postulate 2. In this course, we'll generalize postulate 2. Well, let me go over first. So it's about measurement. It's a measurement postulate. It says that when observable A, that we saw is a Hermitian operator, is measured in some ket state psi, the probability of finding an eigenstate A prime corresponding to the observable A is the bracket of A prime and psi squared, or norm of it. And after the measurement, the state, the ket, is thrown into another ket, which is the eigenket corresponding to the prime. If you are degeneracies, the story is a little bit more complicated, but let's not worry about that for now. Right? So what we're going to do today, by the end of the day, is we're going to generalize this to describe measurement for density matrices. A small note here is that I'm not going to present the most general measurement postulate for density matrices for the sake of the fact that this is like we don't want to jump into all the complexities at once, right? So I'm gonna still present a rather limited context, all right? Still more than what most textbooks discuss, and something that's absolutely essential for doing physics these days. All right, any questions? So by now, density matrix should be synonymous with a state in quantum mechanics, right? A density matrix or density operator. The terminology is, they mean the same thing. Good? All right. So let's motivate the density matrix. Let's motivate why we need to go beyond kets. The argument I'm going to run is rather profound, but at first it might seem a little bit silly. Well, not silly. It might seem like, okay, what's the big deal? But we'll gradually, you'll get it. So recall the Stern-Gerlach experiment, right? What was it? We had a beam of silver atoms coming in. We measured some z components of the spin, and there were two possible outcomes: +1, which is plus h bar over 2, or minus h bar over 2, right? Now, what we said was that here, let's pass through only the ones that come up with plus h bar over 2. So +1 eigenstate. Next, let's measure S of x and this ket. What is the ket that describes the state now? Sorry? Yeah, so the ket here is just plus, right? SD plus 1 or plus. Now, what we said here is with probability half, this comes up to be Sx plus, and with probability half, it comes out to be Sx minus. All right, let's just think a little bit deeper about what the hell does this mean? With probability half comes up here, probability half comes up here. What does it mean? Let's say I have a single atom. I send it through, it comes up here, okay, so this get. Then I send it through this, right? How do I measure probability half? Can you measure probabilities? How would you interpret? If I tell you I have a coin that with probability half, it's coming heads and probability half, it comes at tails. What does that mean to you? Yeah. Very good. So this is precisely the core idea. So there are two attitudes toward probability. There are only two attitudes toward probabilities. One of them is a frequentist. So you're a frequentist, and we're all brainwashed with frequentist. It says the following: if you flip a coin an infinite number of times, the number of times it comes as heads, right, becomes more and more. It goes to half of the times, right? I don't want to make it a more rigorous statement than that. Okay, so this is the frequentist way of interpreting stuff. There's also the inference, but let's not talk about inference, right? So we're going to take that out. Now, if I have a single copy of the system, there's no way on earth I can make sense of this statement. Let's let this sink, right? There is no, you see, this is not my lack of knowledge. It's probability half. It's not because I'm a crappy experimental. I'm a terrible experimentalist and my devices are bad. This is inherent to nature, right? So I have to come up with a way of describing this. The only way to interpret this is that I say I have a whole bunch of silver atoms that I send, many of them. And the ones that come down, I discard. Now I have a beam of silver atoms that they all came up. This beam is like an Avogadro number. It's like 10 to like gazillion number of particles. And now I know they're all prepared. All of them are prepared identically in the same damn state, ket plus. Now, if I do this measurement, I'm doing this on many copies of the same state. They're all identical in the same ket. Now I can make sense of this statement. Good. This is the only way to interpret this. I'm going to pause to see if this is okay. So what I have is what a physicist calls an ensemble of states. Many copies or many particles. Each of them are in some state, right? So it's a group of particles. And they're all, in this case, they're all prepared in the ket SD plus that I wrote as ket plus, right? Every atom in this beam is in this state. Yeah.
You're saying ensemble, but in like statement, we have microstates corresponding to like some the same macroscopic variable.
So very good. This is a notion of, you're pointing something very deep. It's a notion of ensemble. The notion of ensemble in classical physics has to do with the fact that I have macro observables because my measurements are imprecise. Here, the notion of ensemble is because of quantum mechanics. You don't, here, it's a must. Doesn't matter you have macro or micro or any crap like that. It's just, ensemble is all you've got. This is what I'm trying to describe to you guys. This is extremely crucial. In quantum mechanics, there is no way around this. You're always dealing with ensembles. In classical physics, this was like, I don't know, maybe I can measure certain things, maybe I cannot measure certain things. But this is inherent to nature. All right? So, all right, the next step is, what if we measure the beam Sx, but we keep both of the outcomes, right? So now, what I'm gonna do is, I'm gonna, like here, as I measure the ones that come up, right? I'm gonna keep them. I've measured them. The ones that come down, I'm also gonna keep them. So what do I have? I have a beam of lots and lots of silver atoms. Half of them are in the state Sx plus. Half of them I said Sx minus, right? There's no way for me to say this individual. Well, I don't want to say that. My best description of this ensemble after this measurement is with probability have this ket, with probability have this ket. At this point, what I'm trying to highlight is that this is classical probability as opposed to quantum stuff, right? This is because I probability have this, probability have this, right? This is what I meant by saying that this innocent sound, but it's going to become deep. So what I would like to have is I would like to have a description of a state which is, or beam which has 50% of the particles are in ket plus 1 and 50% are in ket minus 1. I encourage you to think very deeply about this, and it's a very productive thought because in quantum mechanics, I assure you, this is not what you expect, what it looks like at the first look. It's a little bit deeper. So this is some classical probability, right? With probability 50%, I'm in some state, ket plus 1, Sx plus 1, and probability half in ket Sx minus 1. So I'm wondering whether I can describe this state I just described, this state, using a ket, right? Can I describe a beam that's half up, half down using a ket? That's a question. We're going to see that it's impossible. So I need to invent new things, right? So this was superposition. And the point is that it's distinct. Superpositions are distinct from classical probabilities. If I measure this ket alpha, what is the probability of getting Sx plus 1? C1 squared, right? C1 squared. What's the probability of getting Cx minus 1? C2 squared. So you might think that, oh, if you put this half, for example, you pick some state like this. Maybe this is the ket that describes your beam that's half from up, half down. The answer is no, and we're going to see that in a second. As you probably know, I can put an arbitrary phase here. The probabilities don't change. Whereas, these numbers are complex numbers. Here, I'm dealing with positive probabilities, right? It takes a while for it to sink. But the cleanest way of seeing like having a quantum mechanics in your face is by talking about the expectation value of an observable. So I'm going to compare two scenarios. Scenario one, when I'm looking at the expectation value of an observable, maybe, yeah, I think, let me change my notation to make this a little bit more dramatic. Actually, you know what? No, let me not do it now. All right. So let's first take this ket, right? What is the expectation value on observable A in it? Well, you will have to take this A, this alpha, put observable A, and then takes this guy and takes the complex conjugate of it. You get 4 terms. You get the term which is coming from C1 and the same guy. Is this clear? Can you see the 4 terms? All right. So one of them is C1 squared that has +1 on both sides. One of them is C2 squared that has -1 on both sides. These look like probabilities, but you have 2 extra terms. These are phases, generically. If I were to compare the state with the ensemble that I was describing, let's call P is C1 squared and 1 minus P is C2 squared, because probabilities have to add up to 1. Now, if I have an ensemble, which is with probability P Cx plus 1 and probability 1 minus P Cx minus 1, I only reproduce the first two terms, but the next two terms are absent. The next two, those two terms, the red ones, are crucial for a phenomenon in quantum mechanics called interference. This phenomenon that we went over, that whether you watch the system or not, it changes the result. So when you have probabilities, we call this an incoherent mixture. Whereas over there, we call that a superposition. All right, let's pause. Is this clear? It shouldn't be. So, if you have not seen density matrices, this is kind of a leap. Ask questions. Something. Yes.
Start by saying the cluster problem but in some sense, if I gave you a state with solution of C1 plus C2 minus and get a measurement of it, you still get the same output, right? So how do you conclude that it's cluster property or is it?
In one measurement, I will get the same output. However, if I sequenced, recall what we did with Stern-Gerlach, we did SZ, SX, SZ, you're going to see the difference. So I encourage you to do that. These two terms are the origin of all those weird, not all, but like some of the weirdness of quantum mechanics has to do with these two terms, right? So at the very least here, what I'm arguing is that I have a state that I cannot describe using Ketz. This is what I'm trying to establish, right? And yeah.
This would be more proof for the SC
SZ eigenvalues.
because if you just had SX,
yeah.
or are you seeing the initial statement of the X?
Yeah, it doesn't matter what observable it is that you're talking about. I can have an observable can have a couple of outcomes, right? Now you could have a superposition of so each outcome has an eigenket. I can talk about the superposition of eigenkets, or I can talk about a probability having a state which is with a probability P1 in the first eigenket, P2 in the second eigenket. These two are distinct physically. That's the point. And now, if you're wondering, like, why on earth am I even talking about, like, the probability of half up, probability of half down? You would be right, because up until the 80s and 90s, the textbooks that were written thought this was not a big deal. If they thought that if it just comes up if you wanted to do statistical quantum mechanics, but that's a little bit naive, right? So I hopefully argued for you that the very statistical probabilistic interpretation of quantum mechanics forces you to consider such states. It's not the question that came up ensemble. It's not about that I have some coarse-grained, rough observables that I didn't do a good job of measuring. It's just inherently, it's in your face. Ensembles are inevitable in quantum mechanics. It's not your choice. Entanglement, this objection of Einstein, precisely had to do with this. We'll get there. So hopefully these words will help at least some of you guys. In classical physics, probabilities and ensembles have to do with coarse grain, has to do with macro observables, has to do with the fact that my measurement devices are low quality or bad or not perfect. In quantum mechanics, ensembles have are not necessary. You can have ensembles without coarse grain. Exactly, that's the statement. You always have ensembles. You don't need coarse graining to have ensembles. Ensembles are in your face. You must deal with them. So that's the sense in which in quantum mechanics, there's not much difference between talking about an individual state or doing statistical mechanics. Quantum stat mech is quantum mechanics. There's not much of a leap there. Good. All right, this will take a while, I imagine. But the way for this to click is to do calculations. That's why we're gonna have a few longer homework, and you absolutely have to do these calculations to see these two extra terms come up and give you hell. Like these two terms should appear in all sorts of places. All right. So more generally, if I have a set of eigenkets alpha of I, let's say they are orthonormal, right? With each with probability correspondingly pi. If I have an ensemble, which is with probability pi in ket alpha I, the expectation value of observable A, that's not a nice notation. This is notation Sakurai invented. I'm just writing it for now. You're going to see what the actual notation is sum over pi expectation value of A alpha. Good? Is the first line, is everybody with me on the first line? The expectation value of A in eigenket, or in ket, pure state ket, alpha I is that thing. With probability pi, you have that thing, so you sum over them to get the expectation value. This step is classic. Now, insert a resolution of identity for your favorite observable B. Those B prime sum over B prime. Right? Now, what you could do is you could rearrange this, right? Just bring this guy to this side, this guy to this side. And then you notice that you could repackage the whole thing as this is sum over B prime, oops, B prime, B prime. If you recall, sum over B prime is trace. If I define this operator, this is an operator, this is a matrix, as the density matrix, as the state, now I can write down the expectation value as trace of A row. So the density matrix is this. So what did we do? We said, if I want to describe ensembles, I can describe them using matrices. My notion of expectation value, which was just a bracket in the past, now becomes trace of A row. So the expectation value observable A in density matrix row, state row, is trace of A row. Yes.
So the trace of A, that's a row, and then the density, the last line is row equals.
Yes.
That's
It's a yeah. A row is equal to sum over I pi. Sorry, I think.
the only two rows are
Yes. Sorry about that. It's row pi. I think that's why I was wondering why Sakurai uses WI. In quantum mechanics, we use P and rho all over the place. Right? So this already should give you a reevaluated version of like things. Now your states are operators. They are D by D in D dimensions. They're D by D matrices that have the following form. And if you want to observe, look at the expectation value of an observable A in these states, you have to take the trace of A row. Why did I not write trace of row A? I could have. Because they're equal. Trace is cyclic, if you recall. Trace of AB is the same thing as trace of BA. So the density matrix is, by the way, so now you remember, so what is the density? Sum over I, pi. So it's a sum of a bunch of terms. Each term is what? Ket alpha I, rho alpha I. You've seen this operator before. What is this object? We gave this a name. Projection. It scores to itself, it's self-adjoint. If we check that. So now you should totally see already that what is the density matrix that corresponds to a ket, that describes a ket? Can you tell right away? If my PIs, one of them is 1, the other ones are 0. Right? That's a ket. That's an eigen. So an eigenket looks like this state. This is a density matrix corresponding to an eigenket. All right, let me do a little calculation for you guys to convince you that this makes sense. So the density matrix that describes a ket alpha, this is I guess rho of alpha is this guy. So if I want to calculate the expectation value in observable A in the state, what should I do? I should calculate trace of A rho A alpha. What is that? That is sum, actually, that is trace of A ket alpha alpha. Write the trace as sum over BB prime this way, right? Bring this term here, swap the two terms. You see a resolution of identity in there, you remove it, you obtain right. This is just basically reproducing that step. Just swap the two terms, you're going to get a resolution of identity. Should I do that? Or do you see it? See it? Okay. Questions? Of course, any generalization we make, it should be consistent with what we already knew, right? So this formalism should include kets as special states. What are those states? They look like this, right? And everything goes through. The expectation values are as before. All right. So now a bunch of things. We said that PIs, oops. So in general, rho as a density matrix has the following form. I don't know what I'm doing here. Okay. Sum over PI, these projection operators. PIs are probabilities. So they are non-negative numbers that add up to 1. That's what the probability measure is. Good. What is trace of rho? Let's calculate it. I have to take the oops. I have to take the trace. If I want to take the trace of rho, I just have to write sum I pi. What's the trace of a ket bra? It's the bracket, the corresponding bracket. You just flip them. Yes. So these are, I said, an orthonormal basis. These are just orthogonal vectors. You could cook up an observable for which these are the eigenstates. What is that observable? Can someone tell me one observable that these are the So I have a list of orthogonal vectors, orthonormal vectors. How do I write mathematically that they're orthonormal vectors? Yep. And their product is delta H, right? This is an orthonormal basis, right? Now, tell me how to write an observable for which these are the eigenkets. Sum over I, alpha i's, your favorite numbers here, right? Clearly, if you act with this operator, just do it. Just check it. It's a linear algebra. If you act with this operator, call them whatever you want. I don't know. Some lambda i's, right? If you want an observable, what properties should lambda I have? Real. Awesome. Good. All right. So if you take the trace of rho, you find it's 1. Is that so clear that trace of rho is 1? So a ket state that's described by ket is called also a pure state. it's a density matrix that could be written as some alpha, check alpha psi alpha. It's a projection of dimension 1. I haven't described it what dimension alpha is. But basically it corresponds to density matrices where one of the probabilities is, let's say the first one is 1, the other ones are 0. Right? These are called pure states. They satisfy the following property, rho squared equal to rho. I can write them this way. On a particular basis. Can you see why rho squared is equal to rho? For these kets. Let me do it on the board. So now I'm talking about special density matrices that are described by kets alpha. So these are the corresponding density matrices. Let's calculate rho alpha squared. So what is that? Alpha, 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 alpha. What is this? It's 1. So this is alpha, alpha, otherwise known as rho alpha. So what is trace of rho alpha squared? What is the trace of alpha squared? 1. All right. So let me summarize here. No, actually, let me summarize here before going to the next slide. What did we say so far? This is a summary of it. You're going to go over these notes and you're going to read about this. You're going to learn about this. A general state in quantum mechanics is a density matrix. It can always be written as a sum I, pi, a bunch of kets alpha i's, right? Of this form. Oops, this form. For some ket alpha i's. All right? It has the following property that the trace of rho is equal. So this is a basis dependent statement. Trace of rho is equal to 1. We're going to go over a bunch of other properties of the density matrix. But when the density matrix is describing a ket, the states that you're used to from the previous lectures, they have this further property. The trace of rho squared is also equal to, rho squared is equal to rho, right? Equal to 1. A trace of it is 1. Why is rho squared equal to rho? Because I said it's a projection. You knew that, right? A projection scores itself. These states are called pure as opposed to non-pure states that are called mixed. Yes. Only for pure states. So actually, let me say it right away. I was gonna wait for a bit. If I give you a density matrix, the quickest way to know whether it's describing a pure state is to calculate trace of rho squared. It's trace of rho squared is equal to 1 if and only if it's pure. That's for that reason, trace of rho squared is called the purity measure. It measures the purity of the state. We're gonna say that in a second. Does anyone can anyone guess already what is this? For a mixed state, is trace of rho squared larger or smaller than 1? Let me see that. What is trace of rho squared for a mixed state? Okay, we'll do the calculation. That's all linear algebra after all. But let me pause here again. Are there any questions? Let's see how I'm doing in time. All right, I'm doing well. Let me make sure this clicks. This is very, very crucial. When you do your homework, you'll also see that. I'll work out a bunch of examples as well. I said a density matrix. I said that this is a density matrix, right? And any operator that looks like this is also a density matrix. These are probabilities. But this description is basis dependent, right? I have to give you a basis independent way of describing the density matrix. Is that clear? This is basis dependent. So in this basis, what is the density matrix of the matrix? Can anyone tell me? Yes. P1, P2, PD, the D by D matrix. This is a diagonal matrix with P's on the diagonal in this basis. Now, of course, I can write this in my favorite basis. So don't expect density matrices to be diagonal. That's a basis dependent statement. If I give you a density matrix, the quickest way to know, well, okay, no, never mind. I didn't say that. I haven't told you that. So in this basis, what is the pure state? I have it on the board. 1, 0, 0, 0, 0. Or a 1 anywhere. Right? Anywhere on the diagonal. Now it should be clear why. So now it should be clear what is trace of rho squared for a mixed state? What is rho squared for a mixed state? Right? When is the sum of a bunch of probabilities squared equal to 1? Only when one of them is 1, the other ones are 0. A bunch of probabilities, if you square them before summing, that thing is always smaller or equal to 1. Definitely convince yourself that's true. Is equal to 1 if and only if one of them is 1, the other ones are 0. Right? By the way, trace of rho squared. Now, I just said sum over IPI squared. Right? This is basis independent. Why? Because trace is basis independent. Even if I gave you the density matrix in some obscure basis where you could not see PIs in there, it's just some obscure basis. If I calculate trace of rho squared, I can recover the sum of these guys squared. That's why this is a good measure. It's called purity. All right, quick test of these ideas. If I, instead of trace of rho squared, if I looked at trace of rho to the power of 15, what is it for a pure state? 1. What is it for a mixed state? Less than 1. So purity is just the second power. The other ones are the same. I don't have any of you guys heard of LP spaces? Mathematicians in linear algebra study these, are called LP spaces. It's like undergraduate level math. All right. Any questions? Yes.
So do your higher square of your row, they have any significance?
Physics. That's a question. Physics. Oh God. Yes, they do, and I can tell you that this it's only quantum mechanics is from like early 20th century. It's only in the past 10 years we have managed to measure rho squared, trace of rho squared. This guy. Actually, one of the guys who did the first measurement of this guy, this trace of rho squared, works here at Purdue. His office is across from mine, Alex Mock. They did this at Harvard or Chicago, I don't know. But yeah, so it's very new. It's past 10 years that we've learned the physics of these guys. The mathematics of it and the quantum information side of things, a little bit older. So I don't want to pretend that this is just a recent discovery. But really measuring this is very, very, very recent. We're talking about, like past 10 years. Yeah, there are significance, but let me not go on tangents. Yes. Oh yes, 100%. Yes, yes, absolutely. You're on the right track. Yeah. Did everyone get that comment? All right, let me know. If you have extra time, I'll comment on that. I'll come back to that. There is, regarding your question, I can, well, if you have time, I'll comment on, I'll relate it to some physics you recognize. Namely, macro-canonical ensemble versus canonical ensemble. Well, we'll come back to that. This is the quantum version of that. But, all right, let's go ahead with let me get through the material I've prepared. So more generally, a density matrix looks like this, as I said. And it means that if you take the row squared, I know that my rows look like p's, so sorry about that. Then this is sum over ij, pi, pj, alpha I, alpha j. What is this? It's delta ij. So you get rid of one of the sums, you end up with sum over I, pi squared, alpha I. Trace of row squared of that is sum over I, pi squared. That's less than 1. I just did that on the board. It's also equal to 1 if and only if one of the probabilities is 1, the other ones are 0. In that case, we call the state pure, and we can equally describe it using an eigenket. Sorry, a ket. A ket, I shouldn't call it an eigenket. Trace of row squared is called purity. Yes. Is what? Yeah, this is an orthonormal basis. Actually, let me do one. I'm gonna have examples to see. I'm still doing it everything in a trivial basis. I'll show you how things get a little bit more complicated. Good. All right. Property. Oh, actually, wait a second. Let me do the example now. All right. A quick set of questions for you guys. Is this density matrix mixed or pure? It's pure, right? If I write it in SZ basis, what does it look like? What was the ket plus in SZ basis? It was 1, 0. What is the bra of it? 0 and 1. What do you get if you multiply them? 1, 0, 0, 0, 0. Voila, this is a density matrix. There's probabilities are on the diagonal. 1, 0. Pure. Good. Is this density matrix pure or mixed? It's also pure, right? But what does it look like if I write it in the SZ basis? What was the ket SX plus in the ST basis? Do you recall? This was SX plus, which you could write down as 1 over square root 2, 1 over square root 2. Good? All right, so let's calculate this. What is the bra? It's the same thing. 1 over square root 2, 1, 1. So when you multiply them, you're going to get the following piece. You're going to get half, 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 half. Given this matrix, how would you know it's a density matrix? How do you know? This looks like some matrix, right? There are a couple of ways to know whether this is a density matrix. One simple way of saying whether it's a density matrix or not is to find its eigenvalues. Right? What are the eigenvalues of the density matrix? Yeah, the probabilities. That's why I wrote it in that basis, right? The probabilities are the eigenvalues. So if I calculate the eigenvalues of this, I should have 2 eigenvalues. One is 1, the other one is 0, right? I know it's a mixed density matrix. It's a pure density matrix. So don't be fooled don't expect all of them to appear like this. Good? So that was the point. Now, this is a question I was asking people when, anyway. If I give you a matrix, how would you tell whether it's a density matrix? Let's go over the properties of the density matrix. A density matrix is Hermitian. Why is that? Well, take the diagram of that thing, right? The sum over IPI, what's the diagram of projection? Itself. So it's Hermitian. That means that its eigenvalues are real. But you knew more than that. You knew that the spectrum of rho is non-negative. Right? So the eigenvalues are non-negative. I don't know, you want to call them positive or non-negative. I always get confused with this. I always call them positive. I think positive is semi-definite or things like that, right terms, but I never understood. The eigenvectors of rho are these alpha i's, and their eigenvalues are pi's. Trace of rho has to be equal to 1, which means that the eigenvalues have to add up to 1. So there are 3 properties we listed. Based on these 3 properties, a density matrix is a positive operator with unit trace. What is a positive operator? A positive operator is an operator whose spectrum has a bunch of positive, non-negative numbers. Good? That's the very definition of a density matrix. The idea of positive operator is very, very fundamental. So let me make sure everybody understands this. So density matrix is a positive operator. Not only self-adjoint, it's Hermitian, but also Hermitian means its eigenvalues are real. On top of that, its eigenvalues are non-negative. So it's a positive operator. Positive operators are physically distinct. They're very, very important. What's the name of the positive operator you recognize? All of you guys recognize in physics. As physicists, what's a positive operator? What's a positive observable? What is it?
Harmonic oscillator
Energy. Energy. In physics, one would like the energy to be bounded below or be positive. Right? There you go. Hamiltonian is your positive observable. That's one of the most fundamental ideas of physics. All right, Hamiltonian is positive. Well, okay. I'm not gonna bug you. All right, so the density matrix is a positive operator with unit trace. Does that work? Everybody's happy with that. That's, as a matter of fact, the definition. Because it's basis independent. All right, here are a bunch of examples. I went over them, but let me do them again. So the how are we doing on time? Okay, I'm good. Consider the ket plus. I said that the density matrix is plus plus, and the z basis, that's 1 0 0 0. This is a projection operator. It's pure because rho squared is equal to rho. Now ket, take the eigenvalues that are ket sx plus minus. So I just did the plus one. Let me do the minus one as well. So if I did the minus one, there will be a minus here. Which means a minus here. So where does the minus go? Minus comes here. Minus comes here. Minus comes, well, let me just do plus minus because I did plus minus. Plus minus, plus minus. Okay, this is hopefully obvious. A positive operator can have negative matrix elements. Sure, not the problem, right? All right. Consider sigma x. What was the sigma x as a matrix? Pauli x. Good. What are the eigenvalues of it? Actually, let me do the half so that it's canonical. As 1 and minus 1. it's a Hermitian operator, it's an observable. How can I make it a positive operator? Make a suggestion to cook up a positive operator out of sequence. Sorry? Very good. Square it. That was not what I was thinking, but it's the correct answer. Squaring it is always, square of an observable, right, is always a positive operator. Beautiful. Right? Now, I was going to say something else. I was going to do this. So the eigenvalues of this are +1 and -1. What are the eigenvalues of the identity over 2 matrix? Oh, sorry, I don't want identity over 2. Identity matrix. What are the eigenvalues of it? Just one, right? It's maximally degenerate. So what are the eigenvalues of this guy? Can you see what the eigenvalues are? When I say the eigenvalues of this is +-1, it means that I can write it as a unitary dagger, 1 minus 1. This is the basis that diagonalize it. All right. So let's add identity to that. But identity, you know that it's the same as u dagger u as well. These are unitaries. So I'm going to write this as u dagger. So what is this? This is u dagger identity plus 1 minus 1. Well, let me just say 2 because I actually did not. No, actually, no. U dagger. What is that? This is U dagger. The matrix 2, 0, 0, 0. U. Right? What are the eigenvalues of this matrix? 2 and 0. So it's positive. So by adding identity, I can shift the eigenvalues up. Right? This is a trick we use in physics. If your Hamiltonian is non-negative, you can shift it up by adding identity. You could also check that this this density matrix rho is pure because you calculate rho squared is equal to rho. What is rho to the power of 17 for a pure state? It's still rho. All right. So the third example, it's a state which is with probability a third, the density matrix, with the probability third is in ket plus, with probability 2/3 is in the ket minus. So in the SZ basis, it looks like that diagonal matrix, third, 2/3. Is this mixed? Well, let's square it. If you square it, you're going to get 1/3, 2/3, 1/3, 2/3, 1/9, 4/9. So if I calculate trace of rho squared, that's 1/9 plus 4/9, that's 5/9, smaller than 1. The purity is less than 1, the state is mixed. What are the expectation value of Sx, Sy, and Sc in this state? Tell me how to calculate it. Say Sz. How do I calculate it? I calculate trace of rho Sz. Right? Here we go. Here's a calculation. You're going to do a million such calculations by the end of the semester. Trace of rho Sc. So trace, I'm going to do the calculation, for example, in the Sc eigenbasis, because I already calculated things. Rho in that basis. What is Sz? 1 minus 1. This is trace of a third minus 2/3. What is this? Well, we can add. Right? The third minus 2/3 is -1/3. 3. You can similarly calculate, oh, there's h bar over 2 that I just. So you can calculate trace of rho sy, rho s z, rho s x, and then rho s x. Questions? Yes. Oh, beautiful, beautiful. There is a state that is maximally mixed. This is a state when your probabilities are all equal, right? That's called maximally mixed. I wasn't going to comment on it, but thanks for mentioning that. Pure states are one end of the spectrum. The other end of the spectrum is maximally mixed. What is the density matrix of a maximally mixed state in d-dimensional Hilbert spaces? 1 over d identity. So if the density matrix is proportional to identity, that's called maximally mixed. This is actually, thanks for pointing that out. I wasn't gonna comment on it, but these are very important states. Does anyone have can anyone throw out a physics name for such a state? Just if you happen to know physics interpretation. You've taken stat. No? No.
Right?
No. Infinite temperature thermal state. Infinite temperature. Yes. We'll get there. All right. Postulates of quantum mechanics. So now I'm gonna revise or generalize, not revise. Generalize my postulates of quantum mechanics to describe states, but more generally. Associated to any isolate, this is postulate 1, states and observables. Associated to any isolated quantum system is a Hilbert space. The system is described by its density matrix rho, which is a positive operator with trace 1. Any state is a density matrix, which is a positive operator with trace 1. If the quantum state is in state rho I with probability pi, the corresponding density matrix is the sum over I pi rho I. Good. All right, and then the rest of it I did not write. I should have written. Let me write the rest of it. An observable A is a Hermitian operator. The expectation, let me just move this whole thing down. The expectation value of observable A in state rho is trace of rho A. Good. What's happened up here? All right. So this is for your knowledge, but I encourage you guys to also keep these in mind. I describe a positive operator as an operator that is has positive spectrum, not negative spectrum. Already the comment came up that if I take any observable and square it, I'm going to get a positive operator, right? In fact, it's more general than that. If you take any operator Q and calculate Q dagger Q, that's always a positive operator. That's, in fact, a definition as well. This is an alternative way of defining it. Any positive operator, any positive operator could be written as Q dagger Q. Another way of defining positive operator is that the expression bracket psi, rho psi, for all vector psi in the Hilbert space is not negative. These are equivalent ways of doing it. I encourage you to check the equivalence of this with the other definition. This is basic linear algebra, but you can never spend too much time on linear algebra. This is for sure. Good. So these are other ways to characterize the density matrix. Now comes the tricky postulate that I said I'm gonna sort of present. Previously, so this is the measurement postulate. I should have a measurement postulate for density matrices. Quantum measurements are described by a collection of projection operators EI. Well, because they're projection operators, now they know they're positive. How do you know that projection operators are positive? What are the eigenvalues of projection operators? 1 and 0. It can't be anything else. So they're positive operators. And they add up to 1. Measurement throws the density matrix rho to this funny density matrix, which is EI, rho EI, here's a projections, divided by that number. What is that number? That's the probability of observing measurement I. This will take some time for it to sync, and I'll include homework problems. But for example, let me do an example. If I'm measuring SZ, there are 2 outcomes, and the corresponding projections are E1 and E2. They are plus, minus, minus. If I have a density matrix rho and I perform this measurement, it goes to, if the outcome is, say this is +1, this is -1, then the outcome is +1. The state falls into plus rho plus over plus rho plus. What is this number? It's the probability of observing this outcome. Why do I divide this guy by this? To make sure my state after the measurement is density matrix. After the measurement, this guy is a positive operator. However, it's not unit trace anymore. I have to divide it by this number to make sure it's unit trace. Again, it will take a lot of examples for these to click. All right, so good. Any questions? Any questions? So, for example, if I measured S of X, how would the story change? So the corresponding E+1 and E-1 are Sx plus Sx minus, right? Oh, sorry, plus Sx minus Sx minus. The outcome 1 for Sx and S minus 1. So these are going to be Sx plus Sx plus Sx plus Sx. This is the probability of this outcome. Is it clear that this is a positive operator? Can you see this is a positive operator? Can anyone prove it on the fly like that? Based on what I've told you, you can prove it. Think of the previous slide if you want to cheat. It's a positive operator if I can write it as Q dagger Q, right? My rho was initial, let me write system proof or something. My rho was positive, I knew that. So let me write that as some Q tilde, dagger Q tilde, right? What am I acting on the left? EI. What am I acting on the right? EI. Good. The dagger of two operators flips the order and takes a dagger of each. So this is equal to Q EI dagger Q EI. Done. Right? This was positive. I could write it as Q dagger, Q tilde dagger. I inserted these two guys. I rewrote this way. Now it's an operator multiplied by its dagger, therefore it's positive. To make sure there's a density matrix, I have to calculate that. The only thing that remains is I have to calculate its trace. It will be a density matrix with trace 1. Calculate the trace of this. You'll find what I put downstairs. That's literally the trace. Why? What's the trace of this? It flips these two guys. You will get 1. This is the trace. I put it downstairs to make sure it's a density matrix. Sorry about that. All right. So with that said, we're at the end of this lecture. Let me summarize, and then I'll probably, I don't have time, but I'll comment something, just put a comment out there about this question about the relevance of trace of root 2 or something. So in summary, what did we do? We generalized our notion of a state. We said we must, if we are to take quantum mechanics seriously, we must talk about ensembles. We must talk about states that are with probability P1 ket 1, with probability P2 ket 2, so on and so forth. Now here's a question, trick question. Oh, it's a warning. If I have a state which with probability P1 is in ket plus, so with probability P1 is in ket plus, and with probability, or sorry, P, half, is in probability half is ket 1, and with probability half, it's in Sx plus. Is this a density matrix? How do I describe this? This is a little bit different from what I described to you guys, because I wrote the density matrix as a sum of IPIs with orthonormal basis, right? This is still a density matrix. But how do you calculate? How do you construct it? Well, let's just do, this is pi plus half Sx plus Sx plus. Homework problem for you guys. Build this matrix, show that it's actually positive, it has unit trace, and everything. So you could also have a probability distribution over states that are not orthogonal. That's also kosher, that's fine. Right? So the way that the states are presented to you are not necessarily nice as always. All right, so in summary, we generalized our states to density matrices. As a matter of fact, now based on what I told you, I can write down a general density matrix in the following form. I'm no longer gonna require these guys are orthogonal. I'm gonna only require that they are unit norm. Right? So this is a general density matrix. Previous thing was also most general density matrix as well. There are unit trace operators. There are positive operators. They describe an ensemble. When the probability distribution, which is in this case, sorry, by the way, if these are orthogonal, these are the eigenvalues of the density matrix. In this example, these probabilities are not the eigenvalues. Hopefully that's clear. Right? Good. So when the state is pure, its purity is 1. The state is pure, meaning that it could be described using the ket alpha. If and only if trace of rho squared is equal to trace of rho equal to 1. Right? And then we said other states are called mixed. And I think I'm out of time, so I will not comment on anything else. But I'll probably throw in a bunch of comments about maximum mixed states and thermal state next time. Any questions? Yes.